Welcome to the talk. And the title for today is New Era of Data Center Networking Technology and through Intelligence-Defined Optical Tunnel Network System, or OPTUNS. And this work is carried out at Delta Electronics and NCTU National Capital University Joint R&D Lab and on Optical Edge Data Center Networking Technology. And I'm Maria Yuang. And then first of all, I show you some requirements and challenges that we face. And so, and especially for 5G use case. And then we show you the current answer, the state-of-the-art answer, and the electrical switching based. And then is that good enough? And so, then if not, and are we ready for optical switching? And then we show you our solution with the OPTUNS. And then, very importantly, an OPTUNS is controlled by SDN-based intelligent tunnel control. And finally, I show you some benchmarking results. Okay, data center for 5G edge computing, and 5G it requires has three very important requirements. Two of them are very related to data center, and one is the enhanced mobile broadband. The other one to support AR, VR, and the 3D video. And then the other one, very important, I think everyone knows that, is ultra reliable and ultra low latency communications, which like self-driving cars. So we need unprecedented bandwidth, and which is 100 times more than 4G. And because 4G, and a lot of them, they define 4G differently, so I don't give you the specific number, but 100 times higher than 4G. And ultra low latency, and end-to-end from the user back to the user, end-to-end has to be less than 10 milliseconds. So therefore, if you look at the current infrastructure, everything is sent to the core and then ultimately computed and processed at the cloud data center, okay? And then, so it incurs very high just propagation delay itself, and then it will fail the requirements. So it requires a lot of edge data center to be equipped near to the user at the edge of the network. This is where we come from. So we need data center edge. Is that good enough? Can we just migrate use the current state-of-the-art technology and move that to edge and make it a little bit smaller? The answer is no, because we face a new set of challenges. And that is two. First challenge, if you remove the propagation delay, the next bottleneck will be the server-to-server communication within the data center. Okay, so that will be the first challenge. In addition to that, and the traffic you face at the cloud is totally different. It's very different from the traffic you face at the edge. Okay, it's more bursty, and then we call it more, has higher locality. Okay, the computation is, the traffic behavior is never uniformly distributed. And so is the current state-of-the-art technology good enough? Currently, we use electrical switching. That's very mature. And then I show you here in the architecture, and this spine leaf data center, spine leaf-based network. Okay, and then you see the top switch is spine, and then the middle one is a leaf, and the bottom one is the top of rack. So top of rack, we always need that at the top of the rack, right, to communicate with the outside world. And then all the transmission is done in the optical domain, and then you need a lot of OEO. Okay, and then we show, and then what are the problems? And size unscalable. Not only that, it's bandwidth unscalable. If you want to increase the bandwidth, you're going to get rid of the box and then buy a new one. And then most importantly, it incurs very high latency. And then here I show you 1 millisecond. That is on average, that's a mean delay. But the bound, it can go up to 50.7 milliseconds. And so remember, and then I said the 5G requirement is like, some people say 1 millisecond, but in reality it's 10 millisecond end-to-end delay. And so this is going to fail, and especially under higher loads. And then because Delta is really well known and by its power innovation. So, and this takes a lot of power consumption, and due to a lot of OEO conversion at every switch. So, so we raise the question: are we ready for optical switching? And then we look: is the optical switches ready? Is the basic critical components like WSS? I don't. Maybe you are not familiar with that. That's a wavelength selective switch. Okay, and then that is currently very mature. You can see more than like 2 to 3 vendors and are doing that, more than that. Okay, it's green technology. It consumes very little power. And then it's very high bandwidth scalability. If I move from 10G to 100G to 400G, and then this key components remains exactly the same. And then the only problem so far, maybe I shouldn't say the only problem, because we overcome the problem. So it's a configuration time. And currently, if you just check with the WSS vendor, and they tell you the configuration, if you config from which input to which output, and which wavelength to, and then to which output, and then that takes probably more than 30 milliseconds. But I think our design just entirely resolved the problem. Okay, and then so before we go to ours is like the third, I categorize it as a third generation optical switching system, and I reviewed the first generation and second generation. And the first generation is, it just makes it very big, okay? It has a lot of ports, and then so that it can support a lot of end users. And so it's not scalable size-wise. And it uses MEMS technology, and then so it really requires greater than 30 milliseconds of configuration time. And then so second generation comes up and says it's a multi-unit interconnect system. It's like, okay, we want to make it scalable, so it use smaller size optical switches to interconnect all the end systems. However, up to this, still the configuration delay is still high. So up to now, and then they all are very successfully applied for circuit switching applications. And then, but now, in terms of where we are going, and it fails to meet the ultra-low latency demand. So let me, here I summarize, and the first generation, second generation, and up to our third generation system, and then in terms of scalability and so on. Scalability is from low all the way to high, and we can build a system, and from size-wise, build this system and incrementally. Not only that, the bandwidth-wise is very scalable. In terms of configuration time, and then it takes 100 microseconds for us to configure the switch. But actually, and then we have even more important innovation behind this, and so that we don't even 100 microseconds. It's just. Actually, we have even something better to show you later. Okay, in terms of wavelength, and then we use DWDMs, and then which provides you 80 channels. And in our test bed, we use 40 channels, but so far, and that can be up to 80 channels. Theoretically, it is 96 channels, but practically it's 80 channels. In terms of control, and then second generation, you started using SDN. And then in our generation, we use SDN+, and I will show you in a minute. So our solution is the Optical Tunnel Network System. Okay, I show you the basic concept. And then basic concept, you have a lot of racks at the bottom, right? And then on top of it, you all have electrical top of rack switches. And now what we provide is OPTUNS. That is, you can consider it is a super highway. And so once you have that, and you see that those color switches, okay, and those all are optical switches, 2 types of optical switches. First, the blue is the first type, and then the yellow one is the second type. They all are optical switches that replace all the electrical switches that now currently used. So it's a superhighway system, and then 2 types of optical switching nodes. And if you're interested, then you can just visit our booth, which is D4, okay, at the entrance. And then you can see we have some demos there, and you can just get some taste and some experience of it. And the novelty is we build optical tunnels. And you say, because there's no OEO conversion, so there's no intelligence in between. There's only like a highway, okay? So how can you allocate different? There are tons of this optical sort of highway. And then this is what we call tunnels, optical tunnels. And so these optical tunnels, and they are, the beauty is that they are proactively controlled. So they don't build a highway when you need it. So then you feel the latency. So for example, we can use only 8 wavelengths to provide 600 tunnels. Okay, so that is that's the beauty of the system. And then let's look at this from the system view. And then on the left-hand side, you see that we have the infrastructure. That's what you just saw. And out of that, that's physical infrastructure. Out of that, we build logical tunnels. And from those like several hundred up to 1,000 tunnels, and then down, we support server-to-server traffic flow. Not only rack to rack, but server to server, okay? And then, so the key is how to allocate the tunnel in the optimum way. And we use SDN-based intelligent tunnel control. And you see that there are 3 key components: tunnel allocation. And then so you see that the first one is tunnel pre-allocation. So we have to pre-allocate, and using very small amount of like 8 wavelengths to pre-allocate 600 tunnels and to set up like an all-to-all connection. So whenever the traffic comes in, and then it will be available. Okay, and after that, you say, okay, is that it? No. Then we have traffic monitoring. The monitor the tunnels in real time, not per second or something. It's per 3 milliseconds. Okay, we'll monitor the traffic, and then we say, okay, if the tunnel, well, let me give you very 2 simple examples. If the tunnel is like overloaded, we split the tunnel. In other words, we create dynamically a new tunnel. But this is done even before it is very, it go over like 90% of the traffic. Okay, so we will not have any packet loss. And then if tunnel is very underloaded, we combine the tunnel. Okay, so that is based on the dynamic tunnel allocation back in the tunnel allocation category. So, and everything is done in a proactive way. Okay, and then this is, we have built this together, Delta Electronics, and we have like a whole, like the software, hardware, a lot of people, engineers, and together with NCTU, and then we built an edge data center with 25 racks. And then we built 25 OADSs, and then 5, the yellow one, the OSIS. Okay, and by the way, OADSs are directly connected to TOR, okay, is add and drop. And then each cluster of OADSs, and if the network goes beyond like each cluster, and then the OSIS, the second layer switches, it comes into play and to interconnect all different, we say, pods or clusters. We build everything from scratch, and then here are 2 boxes, and if you're interested in it, please visit the booth. We have some demo there. Okay, so what are the key architectural design features? And then first, scalable, modular, and then fault tolerance. I don't have time to cover that, and then you can just visit booth, and we can probably just describe something to you. And one very, very important is massive wavelength reuse. Wavelengths can be reused, and then in other words, the same wavelength. We have a very finite number of wavelengths, but if you use wavelengths 1 here, and you can use wavelength 1 here, and 1 here, 1 here, we can reuse wavelength. That's why we can have tunnel pre-allocation using only 8 wavelengths, and so achieving ultra-low latency when the traffic comes in. But during the operation, we have traffic monitoring, and that and then we have dynamic allocation algorithm, and that and optimize the total throughput of the system, minimize or maximize the efficient use of wavelengths, so achieving high throughput. And so that is architecture, and move to SDN. Okay, before we look at our SDN, say, and I want to go over a trend, SDN-Then, now, and the future. Okay, then if you are familiar with SDN paradigm, then you know it's a decoupling the data plane and the control plane, so the network can be very flexible, and then something like virtualization can be done, and then but it's done in a reactive way when traffic comes in, and then they want to do something, they want to set up the path or something, so the complaint incurs very high latency. And what is SDN now? Is the SDN plus paradigm that we are using. And still decoupling, and then the system is equipped with real-time monitoring, and it's a proactive method, and it results in very low latency. And you see the latency is from server to server, from server to any server. It's no more than 140 microseconds, no matter how high the traffic is. Okay, so are we going to stop here? The answer is no. What is SDN plus future SDN plus paradigm? And that is, of course, we need real-time monitoring, maybe even faster, and then faster than 3 milliseconds. And then all the network is controlled and by means of AI automation. So the network, because edge data center the behavior is not just like a cloud data center. And so you can use AI automation in a very, very efficient way right here in this use case. And finally, so that optimal performance can be achieved. So that is SDN plus and plus plus, and that's where we're going. And that's like the system is called Optical Tunnel Network System. So what is a tunnel? Okay, so I show you a lot of tunnel. Tunnel is like highway, and the whole thing is a superhighway system. Tunnel is very simple. It's just an optical path from TOR. TOR is still like electrical, right? And then what we do is populate a flow table there. And then we config the OADS, OSIS come down to OADS, and then finally to TOR. And to config this entire route, okay? And so it's basic transport unit from source TOR to destination TOR. It's nothing but optical path and associated with one specific wavelength. And how can we control the tunnel? And by this SDN plus controller. And then the rest of the OPTUNS, you can consider them as agents. Okay, this controller is centralized controller. And it interfaces with outside world through standard open flow interface. And then the key brain is the intelligent tunnel control. And above it will be some control panel and some dashboard. We show some dashboard in the booth. Okay, so we intelligently control the tunnels in a proactive manner. And what do I mean by that? So we config OSIS, okay, and then we config OADS. And then we make, if this is lambda 1, and so just make a lambda 1 go through that. And then so it will, when packet comes in, just like a highway, okay? And then we add flow table inside of TOR. So very simple. And then, so we can have tunnel pre-allocation. And then traffic monitoring and dynamic allocation. And so in our lab, we have electrical data center network system, and then we use Arista switch, and then compare with our OPTUNS, and then we together we benchmark this on a fair basis, right? So we support a total of 24 racks, and we measure the total amount of power that it requires. And then after computing, and then we can save 82.6 of power. In other words, we use only 18% of the power compared to ESLDC, electrical data center. And then in terms of The second one is latency, as I keep saying that. And remember I said the latency, the mean latency, and that can be up to 1 millisecond. So that is 0.999. You see that. That is the mean latency. Okay. And then, and for us, the mean latency is about 126 microseconds, and no matter how heavy the load. Okay, and then the right-hand side, I show you the delay bound, okay, almost the highest latency. But this is very important for supporting 5G. Like self-driving car, you cannot have any miss, okay, you cannot have any delay in terms of computation and get back to the car. Okay, so the highest delay, the bound is 50.7 when the low is 0.9, not just 0.95 or something. And when it goes above 0.85, and then it shoots up and just goes through the roof very, very terribly. And we guarantee, and then ours is 140 microseconds. 140 microseconds. So the takeaways. OPTUNS serves as a superhighway and tunnel-based system. Okay, no routing but allocation proactively, and then achieves 82.6 power saving compared to electrical one, and then it always guarantees like about no more than 140 microseconds from server to another server within the data center. So it's a promising data center network solution. And finally, I welcome you to come visit our booth in D4, and then we have lots of flyers there, and then we can just have more communication there. Okay, thank you.